Welcome to another podcast. This episode we're going to be taking a look at how to determine equivalence classes. We're going to start by looking at the definition of an equivalence class. So an equivalence class is basically it's a feature of equivalence relations. Whenever you have an equivalence relation, you want to talk about the equivalence classes. So we're going to start by supposing R. So let R be a relation on the set A. Then I'm going to create a new set called the equivalence class of A, denoted by, so then A is the equivalence class for all elements A in A, given by the following set. So it's the set of all other elements in A that the lowercase element a is related to. So it's the set of all B in A such that A and B are related. So you can think of an equivalence class as being a set of all elements that A is related to by R. So it's sort of like its orbit. We'll talk about that when we talk about graph theory, maybe a little bit later in the semester. We kind of think of it as every other element that it's related to. A really good example of this, if I just take some ordered pair examples, is suppose that my relation set consists of the ordered pairs 1, 2, 2, 3, 3, 3, 1, 4, 2, 4, and let me throw in one more pair, the pair 3, 4. Then I want to talk about what is the equivalence class for each of the elements. So let's start with the equivalence class for 1. So the equivalence class for 1 is the set of all elements that 1 is related to. If you look, 1 is related to the element 2, and 1 is related to the element 4. Those are the only ones that we have that are related to each other. So there's the equivalence classes there. 2 is related to what elements? 2 is related to 1, 2 is related to 3, and 2 is related to 4. So that is the equivalence class for 2. What is the equivalence class for 3? Well, the equivalence class for the element 3 is the element 2, the element 3 itself, and the element 4 because it's related to each of those elements. And then finally, the equivalence class for the element 4 is the element 1 and the element 2 and the element 3. Now, there's really not much more going on there than me just identifying which particular element gets related to which other elements. And this is not an equivalence relation. So if you look at the relation R, this is not an equivalence relation on the set A consisting of the elements 1 through 4. However, if we do have an equivalence relation, then special things happen. So let me give you another example that is an equivalence relation. Let me start with, so I'll put in a couple of points here. We'll do 1, 1, 2, 3, 2, 4. I got to have 2, 2 in there if it's going to be an equivalence relation. Let's put in 3, 3. Because I have 2, 3, I'll also need 3, 2. Because I have 2, 4, I'll also need 4, 2. And then let me put in 4, 4. And we'll close it off there. So as it is, this may or may not be an equivalence relation. We need to check transitivity. It's got reflexivity, it's got symmetry, and it has transitivity because 2, 3, and 3, 2, and 2, 2 are in there. 2, 4, 4, 2, and 2, 2 are in there. So it's got transitivity, so we're okay there. This is an equivalence relation. Now I want to ask the same question again. I want to ask, what are the equivalence classes? So the equivalence class for 1 is the set 1 by itself. It's related only to itself. What is the equivalence class for 2? The equivalence class for 2 is related to itself, it's related to 3, and it's related to 4. What is the equivalence class for 3? The equivalence class for 3 is it's related to 2, itself, and 4. The equivalence class for 4 is it's related to 2, 3, and itself. So what's really interesting here is when we have the equivalence relation, the set 1, or the equivalence class for 1, and 2, 3, and 4 all agree, but together they add up to being the entire set. Here, there's no agreement among these. None of them are equal. And this is really made apparent when you start looking at directed graphs. So say, for example, I had the element 1, then its directed graph is to itself, because that's the only one it's related to. But then if I look at the elements 2, 3, and 4, and look at their graphs, they are all related to each other. And they are all related to themselves. So you get sort of this nice closure happening here, and there's something really interesting that's going on whenever we have an equivalence relation. So just keep this in the back of your mind. We're going to look at it in another video, that anytime you have an equivalence relation, there's something interesting that's going on with the equivalence classes, and we're going to expand on that in an upcoming video, but there's a nice sort of closure that these things have in terms of sectioning themselves off. The mathematical name we give to that is a partition. There's some partitioning going on here that you don't see when there's not an equivalence relation. So we typically are only interested in equivalence classes when we know we have an equivalence relation. Alright, I want to do one more example. And the last example here is to look at the mod relation, which means A is related to B if and only if A is equivalent to B mod 3. So remember, A is equivalent to B mod 3 is basically the same thing as saying that when you divide A by 3, the remainder is B, or it's equivalent to B mod 3. One really good way to write this is in this form is B equals 3k plus A for some integer A. For some integer K, excuse me. So what I want to know here is, what is the equivalence classes? And if you stop to look at this for a second and think about the equivalence class A, by definition, an equivalence class for the element A is the set of all elements Z such that B equals 3k plus A, because that's what it means for A to be related to B. So right here, it's the set of all B and A. Well, Z is playing the role of A here. Such that A, B are related. Well, this is what it means for A and B to be related here. So this is the definition of the equivalence class, but it's not really a helpful definition here because I need to determine the values of B that belong to this particular set. And it really depends on what A I pick. For example, if I pick A equal to 0, and I look at the equivalence class for 0, this is the set of all integers such that B is equal to 3 times k. Well, the set of all integers where B is equal to 3 times k are multiples of 3. So this would be these elements. But if I picked 1 for my value there, then this is the set of all integers such that I can express B as 3k plus 1. But these are elements that are equivalent to 1 mod 3. Well, the elements that are equivalent to 1 mod 3 are the elements like -5, -2, 1 of course, 4, 7, and so on. They're basically one more than the elements
B equal to 3k plus 2, which have
a form that they're one more than this
class
previous group.
for 2.
So it would be
like
is the set of all
-4,
elements,
-1,
all integers, such that B is
2,
equal to 3k plus 2.
5, 8, and so on.
And so those are all the elements that are equivalent to 2 mod 3. If you went and looked at the set 3 and started writing those down, then these would be all the elements that are equivalent to 3 mod 3. But this is the elements of the form 3k plus 3, and if you write 3k plus 3, you can write it as 3k plus 1, which means it's a multiple of 3 with a remainder of 0. These are all of these. So if you look at which elements are equivalent to 3 mod 3, they're the same as the ones that are equivalent to 0. And what you notice here is, if you take the equivalence class for 0, add to it the equivalence class for 1, and add to it the equivalence class for 2, every single element's included, and any other elements are just repeats. And that's exactly what happened here with this picture. Once we took 1 and added it to the equivalence class of 2, we had everything in the set. 3 and 4 were just repeats. So it's the same thing in here, in that 0, 1, and 2 are sort of the basic ones, and then everything else are repeats of 0, 1, and 2 in terms of the equivalence classes. Now, we're going to do more with this in a future video where we're going to sort of dive into equivalence classes a little bit further, but I just wanted to showcase the idea of an equivalence class to you and talk about how it depends on equivalence relation, which this mod 3 example is an example of an equivalence relation. So we have this sort of nice partitioning property that's going on here. All right, thank you for watching.